In this video, we're going to revisit recursion relationships, and we're going to go ahead and look at some very famous examples of them. So we have talked about the first one we'll look at, which is the Fibonacci sequence that kind of comes from this famous example about rabbits. Before we do that, let's just kind of throw the definitions out there that we need. A recurrence relation for a sequence A sub n is an equation that expresses A sub n in terms of one or more of the previous terms in the sequence, namely anything from A sub 0 up to A sub n minus 1. Okay, a sequence is called a solution of a recurrence relation if it satisfies the recurrence relation and the initial conditions specify the terms that precede the first term where the recurrence relation takes effect. Okay, let's look at an example, and then I'll kind of come back and review what the initial conditions are after the example. Okay, so here's this first example. Let's say we have young rabbits, one of each gender, on an island, and a pair of rabbits does not breed until they are 2 months old. After they are 2 months old, each pair of rabbits produces another pair each month. Find a recurrence relation for the number of pairs of rabbits on the island after n months, assuming the rabbits never die. Okay, so they kind of help start us off by mapping out this problem. So we start with 2 rabbits, and for 2 months, they just exist on the island and have no babies. But then all of a sudden, in month 3, that pair of rabbits that was here, this pair right here, switches to becoming a reproducing pair and gives birth. Here, I'll pick a different color to this pair. All right. Now this pair is going to go for 2 months before it's allowed to reproduce. All right. However, the original pair is going to reproduce the following month. So this pair again is going to end up reproducing and producing a third pair, this guy. And they're going to wait 2 months before they're able to start reproducing. Okay. Now in the 5th month, the first rabbits they gave birth to become reproducing pairs. And they reproduce and give birth. We'll go with this to this one. But the other one also gives birth to another one. Let's use, how about orange? This one. All right. Now, this original pair is going there, and now that green pair of rabbits, the one that were third born, they're now in the reproducing category. And we're waiting on this little blue one and these orange ones to reproduce, while the yellow one, the green one, and the pink one all produce 3 new pairs of bunnies, and you get the idea. So, this is kind of the map out of what it looks like. And over here, they've been keeping tally. So we start with total pairs, 1, 1. And then they're keeping track of the reproducing pairs versus the young pairs. And then they're also keeping track of the months. Now, what we're more interested in is what's going on with the total pairs. So by month 3, we have started to reproduce, and they produced 2 babies right there. I'm sorry, there's 2 pairs of rabbits now. So they did produce 2 babies, but there's 2 pairs of rabbits. And then we grow to 3 pairs, and then 5 pairs, and then 8 pairs. And of course, we have been looking at this pattern before, the Fibonacci sequence, and we know we add up the 2 previous terms to get to the new term. All right, but we want to show that in general. So we want to show that that's always going to work the whole time, even though it appears to work at the start. Okay, so here's how we show that. So we will start by letting, sorry, I just realized I wrote that really big. Let f sub n equal pairs of rabbits after n months. So we got to give it a label. And we'll typically start these problems like this. Kind of what we're after we give it a label. Okay, so for us, f sub 1 is 1 and f sub 2 is also 1. This, by the way, is our initial conditions. That was the tie up here to the initial conditions. So we have to start somewhere. In this case, it's this first pair of rabbits that takes 2 months before they're actually able to reproduce. So this is the first set, since they can't breed for 2 months. Then f sub n minus 1 represents the number of pairs in the previous month. Okay, f sub n minus 2 is going to represent the number of newborn pairs. Newborn pairs, because a newborn, or each newborn pair, comes from a pair that is at least 2 months old. And f sub n minus 2 is representing pairs that were first born 2 months ago. And those specific pairs are actually starting to produce new bunnies in the next round. So f sub n is going to equal the previous month's pairs plus the newborn pairs. And this is going to occur when n is bigger than or equal to 3, because the first 2 cases for the first 2 months are those initial conditions that we had to set based on the rules. And there you go. That is how you produce a formula in general to show that it's always going to work. So one of these numbers is representing the previous month's pairs that have already existed, and the other one is representing the newborns that are coming along. Okay, let's try another one. Another famous example, the Tower of Hanoi. Okay, so here's a fun little game. And in fact, if you go onto like Amazon, you can find these, the Tower of Hanoi. They're like nifty little wooden games. So it is a puzzle game that consists of 3 pegs and different discs of sizes going from small to big, largest one on the bottom. And here are the rules. You're allowed to move the discs one at a time from one peg to another, as long as a larger disc is never placed on a smaller disc. So the goal is to end up with all the discs on the second peg in order of the largest on the bottom. Okay, so they kind of map out what it somewhat looks like with this little picture. And our goal is to move each of these to, or I should say the whole stack to peg 2. But the rule is you're not allowed to stack a larger disc on a smaller disc. So if I were to move this smaller disc here to like peg 2, in order to move the second disc, I'd have to move it over here first. And then I could take the smaller disc that's on peg 2 and stack it over there when that one is done. A little confusing, but it does make sense. There are games online, the Tower of Hanoi. I gave you a link, and in fact, I'm going to go to that link because it's going to help us with solving this. So before we do that, we are going to need something from a previous section. In particular, we're going to need the summation formula for a geometric series. So geometric series is when you're multiplying by the same number with each new term. Okay. All right, so I wrote the formula there, and we're going to use that. So to start this problem, I want to kind of show you the basics. Before I do that, though, let me go ahead and here, I'm going to move that stupid little marker there. It's going to get mad at me. Sorry. Okay. So H sub n is going to be what we're after. H sub n is the number of moves to solve with n disks. All right. Now to start this off, and this is why I'm going to go to the game to kind of show you, we're going to move the first n minus 1 disks. So H sub n minus 1 is going to occur for the first n minus 1 disks. Okay, so that's what it's going to look like. All right, so all those disks got stuck onto peg 3. And to begin to move this, I would start by moving this large disk over to peg 2. And then I have to start moving the next set of disks again. Okay, the process of moving those previous ones is actually going to repeat itself. I'm going to do the same number of moves I would have done earlier. So Hn minus 1 is going to occur for the first n minus 1 disks. Then we move the largest disk to peg 2, to peg 2. The process of moving the n minus 1 disks from peg 3, to peg 2 uses an additional H sub n minus 1 moves. So here's what we have. In order to move all n disks, I have to do the H sub n minus moves twice, plus moving the largest disk once. So here's what we're going to do. We're going to take this basic formula and we're going to build it into itself backwards. All right. So I'm going to actually shift this over so I hopefully have enough room. So H sub n equals 2, H sub n minus 1 plus 1. Okay, so H sub n minus 1 here, I'm not going to keep writing that each time, could be obtained by doing 2 times H sub n minus 2 plus 1, which equals 2 squared times H sub n minus 2 plus 2 plus 1. That's from distributing the 2n, into the plus 1. Okay. All right, then I'm going to do that again into what I just wrote over here on the right. Okay, into this part. So 2 squared, instead of H sub n minus 2, that's 2 times H sub n minus 3 plus 1 plus 2 plus 1. The 2 and 1 on the outside. Okay, that comes out to 2 cubed H sub n minus 3 plus 2 squared plus 2 plus 1. And this pattern is going to continue. So dot, dot, dot. And here's where we end up. 2 n minus 1 times H sub 1 plus 2 n minus 2. And then it keeps going, actually. Yeah, here I'll do the n minus 3. Why not? Plus dot, dot, dot till we get to 2 and 1. All right. Now, H sub 1 is the very first move, and that happens to equal 1 itself. So I'm going to use a little bit of blackboard magic here because I'm running out of space, and I'm going to stick a 1 in there instead of h sub 1. Okay, so now what I'm looking at, let me switch back to my yellow highlighter. This right here, this is a geometric sequence. And that then can use this formula up here. So here, let's use it. So in this case, R is 2, because we're multiplying by 2 each time. And the buildup starts from here. So like this is the first term, and then the second term, and then the third term, and then now I'm to that term, and then this term, right? Okay, so it's building up from the term on the right. So R equals 2, and A is going to be 1, which means if I plug that into this formula, the sum is going to equal 1 times 2 to the n minus 1 minus 1 all over 1. Which is going to sum up to 2 to the n minus 1. Oh, sorry, this does include the 1. I just realized I forgot to highlight the 1. The 1 being 0, right? 2 to the 0 term. Sorry, so that's the whole sequence. I apologize. So this all equals 2 to the n minus 1 using that geometric summation formula. Oh, sorry, 2 to the n minus 1 minus 1. There we go. Boo, like that. Just kidding. And there, we have figured out how many moves it takes to do that. And in fact, I didn't show you, but it actually on this little game says the minimum number of moves, and that's based on 5 discs. So 2 to the 5 is 32, minus 1 is 31. So it's using that formula to figure that out. Okay, moving on. Next example. Let's find a recurrence relation and give initial conditions for the number of bit strings of length n without 2 consecutive zeros. How many bit strings are there of length 5? Okay, so 2 consecutive zeros. Let's start with that. So let a sub n equal the number of bit strings of length n that don't have 2 zeros in a row. That's what consecutive means. Wow, that's 2 words. In a row. There we go. All right, that's what consecutive means. 2 zeros in a row. Okay, so here we go. We're going to assume that we are working with bit strings of length 3. Okay, because 2-bit strings are very boring when there's just 2 terms. And 3-bit strings is actually when you might start seeing an occurrence of 2 zeros in a row. So there we go. That's our starting point. Okay, so strings of length n have 2 possibilities. One possibility is that it ends in 1. So if it ends in 1, what we're looking at is a bit string that ends with literally a 1 here. And since these are of length n, there would be n minus 1 of these. So there's n minus 1 terms. But what we know is that if there's n minus 1 terms, then this is a sub n minus 1, because this is bit strings without 2 consecutive zeros of length n minus 1. So bit strings of length n minus 1 without 2 zeros in a row. All right. Or the other possibility is they end in 0. Now, when it ends in 0, something special has to happen. And that is, we actually can't just assume 0 is the last number, because the number prior to it can't be a 0. Otherwise, we have 2 consecutive zeros. It has to be the case that it ends in 1 0, which means this time this is n minus 2 terms, or a sub n minus 2. I'm not going to go through the little descriptor. So what we now have is that a sub n equals a sub n minus 1, all the ones that end in 1, plus a sub n minus 2, all the ones that end in 2, and we have a recurrence relationship again. So funny. And we should probably go ahead and note what a sub 1 and a sub 2 looks like. So a sub 1 are bit strings of length 1, one number, and there's only 2 choices for that. It's either a 1 or a 0. Let me just list it down. Those are the 2 options, 1 or 0. A sub 2 is going to have 3 options. Those are bit strings of length 2. So we could have 0, 1, 1, 0, 1, 1, but we can't have 0, 0. That's not a possibility because that has 2 consecutive zeros in a row. All right, so those are our 2 initial conditions there. Now they did ask us to find a sub 5. So let's do that working backwards. So a sub 3 is a sub 2 plus a sub 1, which is 3 plus 2, which is 5. A sub 4 is a sub 3 plus a sub 2, which is 5, plus 3, which is 8. So a sub 5 is a sub 4 plus a sub 3, which is 8 plus 5, or 13. So there's 13 bit strings of length 5 that have no repeating or no double repeating zeros. All right. Okay, so this is another special recurrence relation. And these are the number of parentheses in a product of numbers. Now, note these numbers start with x sub 0 and go up to x sub n. So there's n plus 1 numbers. Okay, there's not n numbers because the x sub 0 counts as a number. And that helps to specify the order of multiplication. So they gave us an example. C3, which is when we're working with 4 numbers, 0, 1, 2, and 3, we could place the parentheses in 5 different ways, and they listed them out for us. Parentheses around the first 2 terms, parentheses around the second 2 terms, parentheses on the first 2 and last 2 terms. We could have parentheses around the middle 2 terms again, but shifting the larger parenthesis, and then parentheses on the last 2 terms. Okay, so there's the rotation of the parentheses. Now, they call this, by the way, the Catalan number sequence. All right. And we want to note a couple important things as we're doing this. So first thing to note when x sub 0, comma x sub 1, comma dot 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 x sub n has parentheses inserted, there is always one multiplication symbol outside of the parentheses, the final set of parentheses. One multiplication always outside the parentheses as the final operator. All right. So it kind of represents the last step, that final multiplication. So in the first one, this one's the final multiplication. This one's the final multiplication. This one's the final multiplication. This one is it, and this one is it. All right. So there's always a final one. Okay. So here's how we're going to do this. We're going to split the sequence up in the middle somewhere. And we're going to say that's where the final one appears. Okay. So let's say the final operator appears. Appears between the x sub k and x sub k plus 1 terms. So these are two generic terms in the middle. So here's how it splits up. We have the first group of terms, x sub 0, x sub 1, all the way to x sub k. And then the second group of terms picks up from k plus 1, x sub k plus 2. And that keeps going until we get to x sub n. All right. So there are c sub k plus 1, or c sub k ways, c sub k ways to insert parentheses in that first set. All right. But over here, we could do that here, but we have to know how many terms there are. And here's how many terms there are. There is n minus k plus 1 terms. So I'm taking the last term and subtracting that first term. N term being the last term, the k plus 1 term being the first term. So another way of saying that is that c sub n minus k minus 1, that's distributing the negative. That's how many ways to insert parentheses. So since the final operator can occur between any two terms, then it follows to list out all those possibilities. And here's how that'll look. So between the first term, c sub 0, and c sub n, c sub n minus 1. So the first term separated from the rest, plus c sub 1, c sub n minus 2. And this pattern continues until we get to the reverse version of this, c sub n minus 2, c sub 1, plus c sub n minus 1, c sub 0. So the idea is this is separating it as x sub 0, and then all the rest of the terms, x sub 1 down to x sub n. How many terms are there here? There's n minus 1 terms. And then the c sub 0 is represented by, I just realized, there's actually n terms over here. So c sub n minus 1 actually represents those numbers of parentheses inserted. And then c sub 0 represents the parentheses over for that one. Okay, so that's how that's being broken up. Okay, but a better way of writing that formula is writing it with a summation symbol. Oops, let me give myself just a little more space on that. Up top, summation symbol, where k is going to go from 0 to n minus 1. We have c sub k times c sub k minus n minus 1. And c sub 0 is going to be 1, and c sub 1 is also going to be 1. So those are our initial conditions that we'll need to go ahead and use this as the formula. And there you go, recurrence relations.